Hello students, how are you? I hope you are all should be fine at your home because it is very crucial time to remain safe and also try to keep your family members also safe. Always confine yourself at your home, avoid movement to outsides because nowadays the spreading of this COVID-19 is increasing day by day. So this is our responsibility to maintain social distance and use mask during the movement and also use hand sanitizer and use some hand wash to clean our hands so that we will be free from coronavirus. So I hope you will be good and happy stay at your home. So today we'll discuss very important topic in this complex chapter. The chapter complex is where now reading. The topic is crystal field theory. In the last class already we have discussed regarding valence bond theory. Valence bond theory only gives the idea about the structure of atom, the covalent nature of complex, and it gives the idea about the hybridization of the complex and the shape of the complex and some qualitative description of the magnetic character of the complex like this. But this theory could not explain the nature of ligands and also the quantitative analysis of the magnetic character of the complex and the stability of a complex, we can say, and what is the actual nature of the complex. Somewhat this theory, crystal field theory, is somewhat better than the valence bond theory. And this theory, we can say, crystal field theory is somewhat, crystals, that is ionic compound, which all are crystals. So the complex compound are considered as a ionic compound as per the crystal field theory that consists of cation and anions. Although it has no free cations, anions, but the properties shows that some behavior shows that the cation part, the metal part behave as a positive sphere and the ligands behave as a negative sphere as per the crystal field theory. Okay, let us discuss what are the features of this crystal field theory. The first point shows that the complex compound considered as a ionic nature. As per the crystal field theory, the complex compound considered as a ionic compound. But the valence bond theory says that the complex compound is purely covalent because it is produced by what? Hybridization concept. So complex compound considered as a ionic compound in which metal ion has a positive sphere, positive ion, and ligands has a negative sphere, negative ion. And the complex is produced as formed by the electrostatic force of attraction between the metal atom or ion and ligands, because metal atom is electron, it is positive sphere, and ligands acts as a negative sphere because ligands donate electron having lone pair. And as the metal ion or metal accept the lone pair, that's why it is a positive sphere, electron deficient nature, and ligands considered as a negative sphere because it has source of electrons. Okay, so complex is formed by electrostatic force of attraction between the metal ion and ligands. And the next point is d orbital of metal atom forming a spherical symmetrical field possessing equal energy among the d orbitals. That is very important thing. Already you have read that d subshell has 5 orbitals. What are the 5 orbitals? Already know the name of 5 orbitals is dxy, dyz, dzx, dx square minus y square and dz square. This is the 5d orbitals D subshell has 5 d orbitals. These are the 5 d orbitals, and the first 3 dxy, yz, dzx, these 3 orbitals are oriented in between the axis. These are not axially oriented. That these are just in between the axis. That means suppose these are the like axes, it will be oriented like this, in between the axis, like this, in between the axis, not along the axis. But these two orbitals are just their lobes are oriented in between, that along the axis. That is dx square minus square dz square along the axis. That means we can say like this. Suppose this is your orbitals. This is one orbital like this along the axis. This is the x axis. This is y axis. So this is the dx square minus y square, the shape of this double dumbbell shape. Okay, these are the 5d orbitals. So these 5d orbitals generally they have equivalent energy. That's why these are called degenerate orbitals. But you see, d orbital of metal atom or ion forming a spherically symmetrical field. That means when the d orbitals remain a spherical symmetrical field, they maintain degeneracy. There is no separation of d orbitals because energy is same. When they maintain spherically symmetrical field, this is very important. When the field is spherically symmetrical without disturbance, then this 5d orbital possesses equivalent energy. That means equal energy you can take. So, but d orbitals in the complex, what happens when ligands come closer to the metal atom, the d orbitals as it is d orbitals as a source of energy also contain electrons. So it is as it is the space where the probability of electron is finding the probability electron is maximum. So this d orbital, what happens, face a repulsion between the incoming ligands, because ligands is coming with electron lone pair. As it is coming with electron cloud having negative charge, when it comes closer to the metal atom, that is the d orbital, as d orbital is more diffuse compared to s and p, then what happens is this d orbital is more diffuse, facing a repulsion between the ligands. When the ligands repel the d orbital, it is just repulsion takes place, then what happens? The d orbital gets splitted. The d orbitals get splitted into different parts. So due to splitting of d orbitals takes place due to the effect of negative spherical field, negative field, that is negative, that we can say negative sphere of the ligands. Due to this repulsion, this d orbital gets splitted into T2G and Eg. Remember, generally dxy, dyz and dzx, this is called as T2G. This is called T2G. And dx square minus square and dz square called as Eg. This is very important, that which is Eg and which is T2G. So this d orbital divided into two parts, T2G and Eg. So this splitting of d orbital occurs, observed due to the repulsion between the ligands and the d orbitals having d orbital having electron cloud and lone, that ligands coming with lone electron cloud. That's why both electron cloud repel due to repulsion. The d orbital is splitted to adjust the increase the stability. Then what happens? These ligands may be strong or weak as per the splitting of d orbital. That is, this splitting of d orbital also indicate the nature of ligands. Which ligand splitting the d orbital more and splitting the d orbital less, it depends upon the nature of ligands. We will discuss later. Ligands may be strong or weak as per the splitting of d orbitals. Stability of the complex also depends upon the nature of ligands used and metal atom and ion also. It depends upon the which type of ligand, what type of ligands are used, are bonded with the metal atom, and and what are the nature of ligands also depends upon the stability of complex. And the splitting energy, this splitting energy of the, when it is gets splitted, T2G and Ag when divided, then it has some splitting energy. This splitting energy depends upon the nature of metal atom, nature of ligands, and also structure of these three things. Splitting energy depends upon nature of metal atom or ions, and also depends on ligand, and also depends upon structure complex. We will discuss later. So this is regarding the features of crystal field theory. Let us discuss the actual splitting of the crystal field theory. But one thing, this crystal field theory generally the splitting of d orbital depends upon three. One is very important is that it depends upon the octahedral splitting, and tetrahedral splitting. And another one is square planar splitting. Three types of splitting. Crystal field theory generally, thus if you see the splitting energy, that it depends upon the shape of the complex, either octahedral complex, tetrahedral complex, or square planar complex. These three types of complex, they have different splitting energy, different splitting nature of the orbitals. So first let us the splitting of octahedral complex. So octahedral splitting. Octahedral splitting, if you see the structure, we know that in octahedral what happens. So this is a 3-axis, x-axis, y. This is your y-axis, and this is your z-axis. If you see in octahedral what happens, ligands generally coming towards the metal atom along the axis. So this is your ligand orientation. Ligands coming towards the central metal atom or ions along the axis. That means axially the ligands attached to the metal atom axially. Axially it is oriented. If they are coming axially, what happens? So if they are coming axially, what happens? Which orbital are axially oriented? Already I have told you. dxy, dyz, dzx, and dx square y minus y square dz. These two orbitals are axially oriented, and these three orbitals are along in between the axis. So are these two orbitals axially oriented? So the ligands which are coming axially, these two orbitals face more repulsion. This is a very important concept in octahedral complex. Why these two orbitals face more repulsion? Because the ligands are attached to the metal atom or ion axially. That's why when ligands coming closer to the metal atom, these two orbitals face more repulsion. That's why as it face more repulsion, its energy increases, and this 3 T2G energy decreases. So we can write like this octahedral splitting. This is the d orbital, 5 d orbitals. This is the 5 d orbitals. This d orbital maintain the energy, equal energy they maintain, but the energy is remaining same without disturbing energy remaining same without disturbance, because up to this they maintain spherically symmetrical field. It is also spherical symmetrical field. It is also maintaining spherical symmetrical field. As spherical symmetrical field, spherically symmetrical field is maintained, so degeneracy is maintained. There is no splitting of d orbital. No doubt energy is increased because it is coming closer, means repulsion starts. When the repulsion starts, then what happens? It also maintains the degeneracy. But when it is very close to the metal atom, then when the spherically symmetrical field will be disturbed, then it will be divided into two parts. This is your T2G and this is your EG. This is called EG and this is called T2G. T2G having 3 orbitals and EG having 2 orbitals. What are the names? This is called your DXY, DYZ, DZX, and this is called your dx square minus y square dz square. Already I have told you these two orbital x square minus square and dz square axially oriented. If the lobes are axially oriented, I have drawn like this. You see, if axially oriented, only this orbital facing more repulsion. That's the energy increases. But it has been observed that these two orbitals splitting energy is much more compared to T2G. So this side will be less and this side more. So this energy gap, this total energy gap, this whole energy gap is called del O. What is the meaning of that? That is octahedral splitting energy. This splitting energy gap between T2G EG, this energy gap is called, whole energy is called delta G. That is called delta G. So how much energy increase? This is minus, we can say 3 by 5 del 0. How much increase? Plus 3. Above means increase. How much increase? Plus 3 by 5 del 0. How much decrease? Decrease value is, we can say right here, that is minus 2 by 5 del 0. You have to remember this. This is the decreasing value, this is the increasing value. Increasing value is much more. How much? Plus 3 by 5, it is minus 2 by. This is the decreasing value, this is increasing value. So this is the, and this difference of T2G and EG called difference of energy. Difference of energy of T2G EG is called CFE, or it is called that is crystal field splitting energy or crystal field stabilization energy. Same thing, crystal field splitting energy, CFSE, crystal field splitting energy, or it is called as crystal field stabilization energy. This is the energy gap between EG and T2G. And this is the diagram of octahedral splitting. Why EG is above and T2 is below, already have explained. All the ligands are coming toward the metal atom and joined to the metal atom axially, so the d orbital which are oriented axially facing more repulsion, that's why EG energy increases, T2G energy decreases. So this is the diagram of what? Octahedral splitting energy. Then if you see tetrahedral, in case of this is octahedral, then in case of tetrahedral, just opposite. What happens? Same thing here, splitting energy will be taken like this, then somewhat energy increases due to the like this, then splitting starts. When the splitting starts, this value will be more and this value will be less. So this will be 3 and it will be 2. And the energy, this will be like this. This will be less. How much? This energy will be delta T. How much? How much? That is 2 by 5 plus. And this one will be minus 3 by 5 delta. You see the difference. Here the difference is like this. Here what happened? You see the difference here. Here energy, decreasing energy is more than the octahedral complex. Here minus 3 by 5, here minus 2 by 5. And this total energy gap, this energy gap is called del T. That means tetrahedral splitting. T means tetrahedral. Tetrahedral splitting, O means octahedral splitting. So this is the diagram. Here d orbitals and this is also d orbital. It maintaining symmetrical field, spherically symmetrical field. That's why energy remaining same. Here the energy remains same. Then you get splitting starts. So this is your tetrahedral splitting. This is octahedral splitting. Then if you see that energy gap. Energy difference between, if you see the energy difference between del 0 and del T, if you compare, always remember that del 0 is greater than del T. This is very important. The energy difference, CFC value of octahedral is greater than CFC value of tetrahedral. How much? It is also calculated. Del 0 is equal to 9 by 5 del T. Del 0 is equal to 9 by 5 del T. It is greater. This much value greater. Okay, then if you see it is being observed that what this splitting energy is more, but the splitting energy this and compared to different, if you compare different complex, this del 0 are different. Del 0 for the all complex are not equal. Del 0 may be less, may be more. It depends upon the nature of complex. It depends on the nature of metal. It depends on the nature of ligands. So many factors are there for affecting del 0 value. But it is observed that this splitting will be more or less. This splitting will be more and less. Then another thing is, suppose you have to fill the electrons. When you fill the electron in T2G and Ag, that if the splitting, it is being observed that the splitting will be more or less. If more splitting del 0 means it is called strong ligand. And less splitting del 0 or del T, you can say both, that is called weak ligand. So ligand may be strong, ligand may be weak, it depends upon splitting. If the splitting is more, that is called strong ligand. If splitting is less, that is called weak ligand. Two types of ligand, strong ligand and weak ligand. That means more splitting means more CFC value. More splitting means more CFAC value. More CFC value. And here less CFAC value. This is the difference. More CFC, strong. Less CFC, weak. This is the difference. So it is already calculated by taking same metal atom, different ligands are joined, and what are the CFC values calculated? You write down the comparison. First order is I minus this is called arranging, that is called spectrochemical series. Spectrochemical series. What is spectrochemical series? Arranging increasing order of CFC value of different ligands. Taking same metal atom. When you change the ligands, then what are the del zero value? What are the CFC value? Then according to this, some different ligands, their CFC is calculated. So as per this arranging this series is called spectrochemical series. Arranging increasing order of CFC value of different ligands is called spectrochemical series. What are the order? I minus, you have to remember, less than Br minus, less than S2 minus. If you remember better, then SCl minus, then which is coming Cl minus F minus, Cl minus F minus, okay, then coming OH minus, OX minus. OX means oxalate, already know, OX means oxalate, then oxide, O2 minus, then here water, these are the water, neutral ligand, then NCS minus, ammonia, then En means ethylene diamine, then NO2 minus, Cl minus, NO2 minus, Cl minus, and CO. So if you see the series, I minus is the weakest ligand. You see the series, CFC value is very less. That's why it is called weakest ligand. And CO is the strongest. Remember, I minus is the weakest ligand and CO is the strongest ligand. Try to remember the series. You have to remember the series for your computer examination. Don't take it casual that this is not required at all. No. Sometimes question will be asked, comparison question, CFC value will be asked. It depends upon the nature of ligands. So what is the position of ligand, which is coming fast, which is coming last, which is coming what after. So you have to remember, try to remember the series. So weakest ligand and stronger ligand, CO and I minus, like this. So on that basis, CFC value is calculated. Then another important part of this octahedral splitting and tetrahedral splitting is that when you fill up the electron in d orbital, is very important. Filling of electrons. Filling of electron in d orbitals. Filling of electron in d orbital. When you fill the electron in d orbital, then which rule you have to follow? That depends upon relation between del 0 and P. If del 0, del O is energy is greater than P. What is the P? P is pairing energy. Pairing energy means energy required to pair electrons. Suppose you see, for example, here, suppose you give 6 electrons, let me 2, 2, 2. So this, if you write 2, 2, 2, that means here pairing is taking place. Pairing means electron generate repel one another. When you add electron in one another electron, so that will be repulsion. During repulsion, energy will be increased. But how much energy is required to add electron to make it pair form? So how much energy required to pair the electron? That is called pairing energy. How much energy is necessary to pair, to make unpair to pair? That is called pairing energy. If del 0, every ligand, every complex has del 0 value, del O value. Del O value and P value, if this compare, if del 0 greater than P, remember this is a strong ligand. This is a strong ligand. Very important conclusion. If del O greater than P, it is a strong ligand. And when it will be a strong ligand, the gap will be more. If gap will be more, then what happens? If gap is more, then how can you fill up electron? Then, for example, you take D6 electron. D6. D carries 6 electrons. 6 electron means either it will be T2G and EG. Total capacity is how much? 10. D6, where you will fill up? As the del 0 is greater than P, so gap is more. More gap. You can write more gap. Between T2G, gap is more. More gap means all 6 electrons will be filled here. So, unit to conclusion will be T2G, as per energy order, T2G coming fast than EG. So, T2G will be 6 and EG will be 0. Then what is the CFC value? I can calculate the CFC value. CFC value will be, you apply this formula. For CFC value, T2G mainly contains 6 electrons. T2G value is minus 2.5. So 6 into minus 2 by 5 del 0. Which EG already 0. So what is the answer? That is minus 12 by 5 del 0. This is the value of CFC value for this case. D6 where it is a strong ligand. Then if the del 0 is less than P, second case, if del 0 is less than P means weak ligand. If it is a weak ligand, then what you will do? Weak means energy gap is less. This is weak. Strong means energy gap is more. If it is weak, then the energy gap is less. We can apply Ohm's rule where, so D6 can be written as T2G first. It will take how many? 3 electrons. 1, 1, 1, then 2, then here 1 will add. Because each will occupy 1 electron as per the Ohm's rule. Pairing will not take place unless and until each orbital is singly occupied. So all 5 electrons T2G, for example, T2G will be 3 and EG will be 2. Then remaining 1 electron will be added here. That's why it will be T2G4 and EG2. Then what will the CFC value? What is CFC? CFC value will be here 4 into how much? Below T2G below minus 4 into minus 2 by 5 plus here EG2 2 into 3 by 5. Answer is how much? So minus 8 by 5 plus 6 by 5, which is equal to how much? Minus 2 by 5. Result is this much. So this is the del 0 value. Minus 2 by 5. Because T2G would carry 4 electron and EG carry 2 electron. Because the energy gap is less. So as per the Ohm's rule, first all will take 1, 1. 1, 1, 1, 1, 1. 5 completed, then next 1 will be added here. So T2G4 and EG2. So 4 means at T2G minus 2 by 5. So 4 into minus 2 by 5 plus how much? 2 electron, 2 into 3 by 5. That is 6 by 5. Here is minus 8. That is minus 2 by 5 del 0 value. Here how much del 0? Minus 12 by 0. That means this energy, if here is minus 12 by 5 del 0, that means more energy is released. You can say this minus 12 by 5 means energy released. Minus 12 by 5. Here energy release minus 2 by 5. This case energy release is more. That's why it is more stable. You can say more energy, CFC value more means stability also more. So minus 12 by 5, here minus 2 by 5. Then another important thing we have to tell, if R ligand is a strong ligand, this is a strong case, this is a weak case, and this is the difference, then how the difference, very important thing now we'll discuss, that if it is a strong, del 0 greater than P means strong ligand, gap is more, so all electron gets paired in T2G, so no availability of unpaired electron. You see, when strong ligand is used, the number of unpaired electron is less. So you have to write here important thing. Let me erase this one. Okay, have you written this one? Okay. If ligand is strong, in case of strong ligand, what happens? All electron will occupy in D first because the energy gap is more. Strong ligand means del 0 greater than P. In this case, all electron will be entered in where? T2G. All electron enter in T2G. That's why strong ligand means unpaired electron is less. So less unpaired electron. Less unpaired means less number of unpaired electron means low spin. That is called low spin. So what is the conclusion? Strong ligand produce low spin complex because all electron will be paired here. But weak ligand means del 0 less than P. Del 0 greater than P means, that is, we can say del O greater than P, that is called strong. If del O less than P, that is weak ligand, in this case more unpaired. Because first electron will be taken by this, all will take one electron, then pairing start. So more unpaired electron available. As more unpaired, that is called high spin. High spin complex. So already I have told you in previous class that who means weak. You see, weak high spin. Weak high spin outer. Weak high spin outer. Another is SLI, sleep. Strong low spin inner. Who? Weak high spin outer, strong low spin inner. This is the what? Two types of complex. Weak high spin outer orbital complex and strong low spin inner orbital complex. On the basis of the nature of ligand, if it is strong ligand, strong means SLI and weak means who. We have to use this one. This is about the concept of the explanation of the actual shape of the molecule, shape of the complex, the magnetic character of the complex, and the nature of ligands, which is strong ligand, which is weak ligands, and how much energy is maintained between T2G, EG, how much, if energy gap is more, then what change takes place, what configuration is changing in the complex. So this concept can be quantitatively explained by the CFC, crystal field theory, CFT. But valence bond theory is a qualitative analysis, only assumptions. Which complex will be inner orbital, which ligand will produce inner orbital, which ligand will be outer orbital. There was no idea. This theory could not explain this concept. But crystal field theory can explain which ligand will produce inner orbital, which complex which will be D2sp3, which will be sp3d2, it can be explained by only CFT. So this is about that modern concept of the explanation of the crystal field theory. Okay, thank you all.